one thing that I wanted to talk about quickly before moving on to solubility is that one thing you can do to help yourself remember that exothermic means that heat is going to be given off versus endothermic means that the reaction vessel is going to get cooled down is you can think of exo kind of sounds like exit, so heat is going to be exiting where the reaction is taking place, whereas endo means in, so heat is going to be going into wherever the reaction is taking place, and that is what we perceive to feel as cooling down. Okay, so let's just tack that on. Exo sounds like exit. So heat is exiting I'm going to call it the system where the reaction is taking place. Which, again, we feel that as something heating up if heat is exiting something. So, like, for example, if you think about a campfire, right? The combustion of the wood is an exothermic process, and if you're sitting around a campfire, you feel that as heat being given off of the campfire. Right? So that's one way that you could kind of remember that exothermic means that heat is exiting the system and you feel it as heat being given off of the reaction. Whereas endothermic, endo means in, so heat is going in to the system, which we perceive that as it becoming cold. All right, moving on to solubility. So there's two terms that you're going to need to know, miscible and immiscible. Okay, so miscible, what it means is that when two substances are miscible, they can dissolve each other no matter what the proportions are, okay, of your solute and your solvent. Now, with miscible, to me that sounds like mixable. So essentially, if one substance can dissolve and mix into another substance, no matter the proportion, it's miscible. Okay, so miscible sounds like mixable. If one substance can mix in and dissolve into another substance, no matter how much you have of each substance, then if they can both dissolve in each other, it's going to be miscible. So some examples is water and antifreeze. Doesn't matter how much you have of either of those, they are going to be able to dissolve into each other. And that's what we would classify as miscible. Same with gasoline and kerosene. Okay, now for the few liquids that don't dissolve into other liquids, we're going to call them immiscible. So that kind of sounds like immiscible or unmixable, okay, because it can't dissolve and mix in with another substance. So some examples of that would be water and oil or oil and vinegar. No matter how much you have of either of them, you're not going to get that oil to dissolve in either the water or the vinegar. Okay. So with differences in solubility, first of all, what is solubility? Solubility is going to be the maximum amount of solute, which is typically measured as a mass, that will dissolve in a given amount of solvent, which is typically measured in volume. Now, a dilute solution is going to have a small amount of solute compared to the solvent. So your concentration of your solute is going to be very small. Whereas if you have a concentrated solution, you're going to have a large amount of solute compared to the solvent, so it's going to have a very high concentration. Now, saturated solutions, that's another term you need to know. That is, I should highlight this, that is when no more solute can be dissolved in a specific volume of a solvent. Okay, so you put in as much solute as you can possibly dissolve. Now, if we were comparing this to something like an unsaturated solution, that just means you haven't put the maximum amount of solute in the solvent. So let's just write that as a note. Unsaturated solution has less than maximum amount of solute dissolved in solvent. Now, with creating saturated solutions, the temperature of said solution is going to be an important part of creating saturated solutions. Okay, so if you're thinking about like a glass of water and trying to dissolve salt in it, you're going to be able to dissolve a lot more salt in that water if you warm it up. Okay, so usually the higher the temperature, the more solute you can dissolve in the same volume. So that applies specifically to most solid solutes. It's going to be a little bit different for gas solutes, but this applies to solid solutes. So usually you can tell that you have a saturated solution because you're going to see a little bit of solid precipitate at the bottom of the container. So a little bit of solid at the bottom of the container. And what's happening here is within the container there is this thing called dynamic equilibrium happening. And that's represented by this reaction, or this reaction equation here. So what dynamic equilibrium means is that your solution, just looking at it, it doesn't appear to be changing, but on a more microscopic level, what's happening is your ions are crystallizing. So they're going from aqueous to solid at the same rate as your solid crystals are dissolving. Okay, and that's what dynamic equilibrium is you have these equal rates of dissolving and crystallization happening. And that occurs in a saturated solution. Okay, so off to the side here, we have a little picture. Okay, so this part right here is our solid solute, which looks like it's going to be copper 2 sulfate. And going off to this way, that's showing that, okay, it is dissolving, it's breaking apart into its ions. So remember, that's specifically called dissociation, which can be a part of the dissolving process. But when we have these ions that are coming together to form our solid, that is called crystallization. When it's going from the aqueous state to the solid state, that is called crystallization. So in special cases, a saturated solution can be prepared at high temperatures and then cooled quickly without crystals forming. Okay? And if that occurs, that solution is said to be supersaturated because you dissolved more than the maximum amount possible, at least at room temperature, in your solution. Okay? And typically, supersaturated solutions are very unstable, and even introducing just one crystal can start the whole crystallization process. So if you wanted to see what that looks like when we have a supersaturated solution and then just adding one tiny crystal to get the crystallization process started, what that would look like is like this. So we have a supersaturated solution in this round bottom flask here. And he's adding a tiny crystal. And as you can see, that has catalyzed the crystallization process, turning our supersaturated solution into just a saturated solution. All right, so moving on to some solubility examples. So solubility, it's typically expressed in grams per milliliter. So just a reminder that solubility tells you what is the maximum amount you can dissolve of a particular substance, usually in water. Okay, and as we said before, it is related to temperature. So solubility is just telling you what's the maximum amount of a substance you can dissolve, usually in water, at a specific temperature. Okay, so if the solubility of potassium carbonate is 94 grams per 100 milliliters, so that's telling you, okay, at 20 degrees Celsius, the maximum amount of potassium carbonate that you can dissolve in water is 94 grams per 100 milliliters. Okay. Now, how much of this solute is going to be dissolved in 200 mils of a saturated solution at 20 degrees Celsius? Okay, so we're still operating at the same temperature. This is our solubility, or a solubility value. Okay, so the easiest way to figure out these types of questions is to set up like a proportional reasoning situation. So if we can dissolve 94 grams in 100 milliliters, basically we're asking how much can we dissolve in 200 milliliters. Now you may be looking at the 100 milliliters and the 200 milliliters and be like, oh, well, since the volume doubled, then that means the amount of solids should also double, to which I would say you are correct. But if we wanted to show how to solve this algebraically, what we would do to isolate x here is we'd say, okay, well, the 200 right now is dividing into x, so the opposite of that is going to be multiplying. So 200, and I should write milliliters here. So those cancel out. And now 200 times by 94 divided by 100, that's going to give us, let's turn that into an arrow there, 188 grams. So again, what we were doing was taking 200, multiplying it by 94, and then dividing it by 100. Okay, and for units, what's happening is since milliliters is in the top and the bottom, those cancel out, and that's why we're left with grams. All right, for the next question, how would you describe 500 milliliters of a solution that contained 94 grams of potassium carbonate at 20 degrees Celsius? So what they're asking is for us to say, okay, is it saturated or unsaturated? So to make this a bit easier to see, let's just take our solubility value and actually take 94 and divide it by 100. That's going to give us 0.94 grams per milliliter. Now if we compare this to having 94 grams dissolved in 500 milliliters, so 94 divided by 500, that's going to give us 0.188 grams per milliliter. So as we can see, this number is bigger than this number. Okay, so if we had 94 grams dissolved in 500 milliliters, that's going to be unsaturated. Okay, because it's less than the maximum amount of potassium carbonate that we can dissolve in water at 20 degrees. So this is an unsaturated solution. So that just means you have less than the maximum amount you can dissolve in a solution, or sorry, in your solvent at a particular temperature. That should be grams per milliliter. So this is an unsaturated solution because 0.188 grams per milliliter is less than 0.94 grams per milliliter, which is our solubility value for potassium carbonate at 20 degrees Celsius. Okay, part C. A solution of potassium carbonate has a volume of 100 mils and contains 50 grams of solute at 20 degrees Celsius. How much more potassium carbonate can it dissolve? Okay, so if we take a look at our solubility number, which is 94 grams per 100 milliliters, we're going to take away how much we did actually dissolve in the particular volume that we dissolved it in. Okay, so minus 50 grams, okay, per 100 milliliters. So essentially what we have left is we can dissolve 44 more grams per 100 milliliters. Okay, so the whole goal of this was just to figure out the difference between your solubility value and how much you actually did dissolve in the water. So what this means is you can dissolve 44 grams more of potassium carbonate in 100 milliliters of water at 20 degrees Celsius. So we have to be specific in the amount of water we have as well as the temperature of said water, because like we said, solubility is going to depend on temperature as well as how much solvent you have. Okay, last but not least here we have how much potassium carbonate in total is in a beaker containing 100 milliliters of saturated solution as well as 10 grams of undissolved solid at 20 degrees Celsius. Okay, so we're going to go back to what exactly our saturated solution is. So saturated solution, which I'm going to abbreviate as SOLN, that just means solution. So 94 grams per 100 milliliters. Okay, and now we also have to figure out, okay, we have an additional 10 grams, so plus 10 grams within that 100 milliliters that we have. So we have 104 grams in that 100 milliliters. So there is a total of 104 grams of potassium carbonate in this solution. That should be a small c. Now, why did we start off with the saturated solution part? Because it told us that we had 100 milliliters of the saturated solution, and like we talked about earlier here, okay, our solubility value for potassium carbonate in water at 20 degrees was 94 grams per 100 milliliters. That's a maximum amount of potassium carbonate you can dissolve in water at 20 degrees. All right. So another thing that we need to talk about in regards to solutions is conductivity. Now, with solutions, there's two types of solutions that we need to talk about in regards to conductivity. So there's electrolytes and non-electrolytes, which are sometimes called electrolytic solutions and just non-electrolytic solutions. Okay, so electrolytes or electrolytic solutions are solutions that can conduct electricity. So absolutely, you should know this term. Now, the reason why they can conduct electricity is because they contain ions. So if your compound can dissolve and break apart into ions in whatever your solvent is, which is usually water, it's going to be an electrolyte. But if it can't break up into ions in whatever your solvent is, then it will be a non-electrolytic solution. Okay, so with electrolytic solutions, those are usually going to be your acids, your bases, and any ionic compounds that can dissolve in water. Okay, And non-electrolytic solutions, those are going to be your molecular compounds that are not acids. Okay, so we'll get into a bit more of that in a little bit here. But right now we got to talk about, okay, conductivity test. What does that look like here? Okay. So first we're going to go over what exactly we're looking for a conductivity test, a positive result as well as a negative result. And then I'll show you a video of what that actually looks like in real life. All right, so if you have an electrolyte or electrolytic solution, which even though it says ionic here, it could be an acid, a base, or ionic compound, which I'm going to add in here that is soluble in water. In water or in your solvent. Typically I just say water because water is the most common solvent. Okay, so if we have a solution which is an electrolyte, we're going to have a positive test. So what that looks like is we're going to have our light bulb, which is part of our conductivity apparatus, light up. And basically what that just indicates is, yep, there's ions present in this solution and it is an electrolyte. So this just means the solution contains ion. That's what that means. Whereas if we have a non-electrolytic solution, which is typically a molecular compound dissolved in water, which is not an acid, we're going to have a negative test. So light bulb will not light up. And so this just tells us there's no ions in that solution. So with our conductivity apparatus, what it's made out of are two electrodes which are connected through wires to a light bulb. Okay, so looking at a video of how this actually happens here. So essentially what this guy has is his conductivity apparatus, which is this stick that he's holding connected to this light bulb, and the light bulb will light up if the solution that he's testing is a electrolytic solution or if it's an electrolyte. So he's got a number of solutions here that he's going to test, and if the light bulb lights up, it's an electrolyte. If it does not, it is a non-electrolyte, and if it's a non-electrolyte, that means that there are no ions present. So testing tap water, you can see that the light bulb lights up. So that means there are ions present in tap water. However, in distilled water, the light bulb doesn't light up. So that means there's no ions there. For sodium chloride, lights up, so there's ions, it's an electrolyte. Hydrochloric acid, it's an electrolyte, so there's ions present. For sodium hydroxide, that's an electrolyte, so there's ions present. For sugar, it does not light up, therefore it is a non-electrolytic solution. For vinegar, that's a weak acid, So the dimmer light says that it doesn't have a lot of ions present in solution. Ethanol, it is a non-electrolyte, so there's no ions present. For barium sulfate, that is insoluble in water, therefore the light bulb isn't lighting up because it's an ionic compound insoluble in water. Okay, so as we've said before, non-electrolytes are solutions that do not conduct electricity. So for the conductivity apparatus, it's not going to light up the light bulb. And the reason being is because they do not contain ions. So your non-electrolytes, those are going to be your molecular compounds, which aren't acids, as well as insoluble ionic compounds. Now, conductivity, as we saw, is measured with something called a conductivity apparatus, which is just electrodes hooked up to a light bulb there. If you are using a conductivity apparatus and the light turns on, your solution that your electrodes are in are an electrolyte, and if it doesn't turn on the light bulb, then it is a non-electrolyte. So strong electrolytes are going to have lots of ions present in solutions, so that's going to cause the light bulb to glow quite brightly. So we saw that in the video with both hydrochloric acid as well as sodium hydroxide. Weak electrolytes only have a few ions, so the light bulb doesn't glow as brightly, and we saw that with the vinegar solution. Okay, so weak electrolytes, those would typically be your weak acids, such as vinegar. And your strong electrolytes, those are going to be your strong acids. They could also be your strong bases. Which I should add on to this. Your weak electrolytes can also be your weak bases. So with factors affecting solubility, if a substance is able to dissolve in a certain solvent, it is said to be soluble in that solvent. In Chem 20 and 30, water is going to be the most common solvent that we talk about. And the solubility of ionic compounds is going to be determined using a solubility table. So with the solubility table that they are talking about, that can be found either in your Chem 30 data booklet or the second page of your chemistry or your Nelson chemistry data sheet. So I'll show you what that looks like on both. So for the Chem 30 data booklet, if we open that up and then keep on scrolling down, oh, there it is. So this is on page 6 of your Chem 30 data booklet here, and it's right near the top. So it's this table in the top half. Looking at our Nelson periodic table, if we go to the second page, it's just in the top right-hand corner here. So this only tells you the solubility of ionic compounds in water at 298.15 Kelvin. And essentially how you would use this table in order to determine the solubility of an ionic compound is typically you first figure out what your anion is, and you look for it up at the top here. So your anion is your negative ion. Now there's not only just anions here, there are some cations such as ammonium, sodium, and hydrogen ions. But the vast majority of them are anions. And what you would do next is you just figure out where your cation falls. So let's say, for example, we wanted to figure out the solubility of, let's say, barium hydroxide. Okay, so what I'd do is I'd be like, okay, what is my anion here? My anion is going to be hydroxide, which I can find right here. Now, what I'm going to do is I'm going to trace my finger down, and I'm just going to see, okay, where is barium? Now, barium is right here, so it is very soluble in water. So where I'm getting very soluble is by looking over here. Okay, so that means when we put barium hydroxide in water, it's going to dissolve. Okay, but you always want to, like, just to finish this example, like if we didn't find barium hydroxide in this first row here, and if it did fall under the category of most, then it would only be slightly soluble, which we basically say it's insoluble in water if you do find it in this last row here. Okay, so that's how you use this table. It's usually you find your anion first, and you find it in the top row here, and then you figure out if your cation's either in the second row here or the third and last row. Okay, so that's how you use a solubility table to determine the solubility of ionic compounds. For having a nonpolar solute, the only thing that's going to dissolve something that is nonpolar is going to be a nonpolar solvent. Okay. For polar solutes, the only thing that's going to dissolve this is another polar solvent. And for anything that hydrogen bonds, you're going to want a solvent that also hydrogen bonds. So as a quick reminder, hydrogen bonding happens in a compound where hydrogen is directly attached to either nitrogen, oxygen, or fluorine. Okay? And these last three parts are just operating off of that principle of like dissolves like. So nonpolar dissolves nonpolar, polar dissolves polar, and something that can hydrogen bond is going to dissolve a lot better in something else that can hydrogen bond. So like dissolves like. And these last three things, those are talking about molecular compounds. So you should be able to determine any compound if it can dissolve or not dissolve in a certain solvent. So just going over some terms that we've talked about previously, a saturated solution is a solution where you have the maximum amount of solute that is dissolved in a given amount of solvent at a certain room or at a certain temperature. And an unsaturated solution is a solution where you don't have the maximum amount of solute dissolved. Okay. Now there's four factors that affect how quickly a solute can dissolve. So particle size. So if you think of sprinkling some grains of salt into water versus throwing a huge block of salt into water, obviously the tiny grains of salt are going to dissolve a lot faster than the block of salt. Okay. Temperature. For solids, if you increase the temperature, you will dissolve more of your substance and quicker. But if we're also talking about gases, Pressure can also help with the rate of dissolving. Okay. So I'm not getting too much into temperature because we will talk about it in a little bit here. And so I'll leave that for later. The nature of the particle. So what that means is your particle ionic and soluble or insoluble in water? Is it polar? Is it nonpolar? Does it hydrogen bond? That sort of thing. So that goes back to like dissolves like. And then last but not least, if you stir your solution, your solute will dissolve faster. Okay, so as promised, we're going into a bit more detail into factors that affect solubility, specifically with temperature. Okay, so generally increasing the temperature of an aqueous solution will increase the solubility of a solute in it. However, it's not always the case. Okay, so for example, the solubility of sodium sulfate actually decreases as the temperature is increased. Okay, now, unfortunately, sodium sulfate here, that is not on one of these solubility curves off to the side here, but that's okay. Now, the effect of increasing temperature decreases the solubility of gases in aqueous solutions. Okay, so essentially what they're trying to get at here is when we're talking about solids, most of the time, not all the time, but most of the time, if you increase the temperature of your solution when you're dissolving a solid solute, typically you are going to increase the solubility. However, with gases, the opposite's going to occur. So with gases, if you increase the temperature, that will decrease the solubility. So for most solids, if you increase temperature, solubility increases. So you can dissolve more in your solvent. However, for gases, so we'll say for most gases, if you increase temperature, solubility decreases. Oop. So that's the main idea that they're trying to say here. Now, with gases, and when you increase the temperature, your solubility of the gas decreases. That is a problem for thermal pollution. Okay, so what thermal pollution is that when you have some sort of industrial plant, like whether it's like a coal-fired plant or a nuclear plant that is situated on a lake, and it takes in the water from the lake to cool the systems down, but then it returns warmer water to the lake. That's thermal pollution, because as you increase the temperature of the water, you're going to have less dissolved oxygen in that water, and so that's going to affect aquatic life, and they're not going to be able to live in that warmer water because there's less oxygen dissolved. For example, when it says if 62.1 grams of potassium bromide is dissolved in 82 milliliters of water at 40 degrees. What is the solubility? So we're being asked, okay, if we can dissolve this, what is our solubility value? Give it to me in grams per milliliter. So literally, we are just taking these two numbers, 82.0 milliliters, and just dividing the two. So we're going to get 0.7573. Number keeps on going on forever. Okay. Looking at the values that we actually used, so these two values, looks like they both have 3 sig digs, so that's what my final answer should be, 3 sig digs. So 1, 2, 3, there's our cutoff line. So 0.757 grams per milliliter. Okay, so just as a reminder, this 0 does not count as a significant digit because leading zeros are never significant digits. A leading 0 is anything that comes before a non-zero digit. All right, example number 2. If we have 39.2 grams of potassium chloride that will dissolve in 185 milliliters of water at 40 degrees, what is the solubility of potassium chloride? So again, with this same situation as example 1, we are just taking these numbers because they're telling us this is going to dissolve. So they're just saying, take these two numbers and divide them to figure out the solubility value. So that's going to give us 0.2118. Number keeps on going on forever. If I look at the two numbers given to me that I actually used, so the 39.2 and 185 milliliters, both of those have 3 sig digs. So I count 1, 2, 3. There's my cutoff line. 3 sig digs. 0.212 grams per milliliter. Okay. Example number 3. At 40 degrees Celsius, how much potassium nitrate can be dissolved in 500 milliliters of water? All right, so for this one here, we need to first figure out what the solubility value is for potassium nitrate in water at 40 degrees, and then we need to set up some proportional reasoning to figure out how much can dissolve in 500 milliliters. The reason why we have to set up proportional reasoning is because this graph does not go up to 500 milliliters of water. Otherwise, we'd just look it up on the graph. So, potassium nitrate, that curve is this one right here. And it says at 40 degrees Celsius. So we're looking right here. Okay, so if I go over to the side, okay, so this is going to be, or the solubility of potassium nitrate at 40 degrees Celsius is going to be 60 grams per 100 milliliters of water. So 60 grams per 100 milliliters of water. And now this is where we set up the proportional reasoning situation because the graph didn't go up to 500 milliliters. So we want to figure out, okay, how much can actually dissolve in 500 milliliters if 60 grams can dissolve in 100 milliliters of water. So isolating the x, what we're going to do is notice how 500 milliliters is dividing into the x, so we're going to do the opposite. So 500 milliliters, what I do to one side, I have to do to the other side. So what we're going to do here is I'm going to take 500 milliliters, times it by 60 grams, and then divide by 100. So that's going to give me 300 grams. Another factor that affects solubility is going to be pressure. So maybe we should highlight temperature because that was one of the factors. The next one here is pressure, which is going to affect gases and nothing else. Okay, so gases, they're going to have higher solubility in liquids that are at higher pressures. So if you increase the pressure, you're going to increase the solubility of the gas. Okay, and essentially what you can do to help yourself remember that is if you think of a can of pop, it's pressurized. Okay, as soon as you open that can of pop, the pressure is going to decrease and the gas starts dissolving out of solution. Okay, so that's one thing you can do, because if you leave that can of pop just sitting on the countertop, right, with that lowered pressure, eventually it's going to go flat. And that's because gases are not soluble or are less soluble in liquids at lower pressures. Okay, so the gas is escaping out of the pop when it's at a lower pressure. The next factor that affects solubility is going to be miscibility, so whether two substances can dissolve in each other or not. So when two liquids mix together, they're said to be miscible. So ethanol dissolves water, meaning that they are miscible. The reason why they are miscible is because both of them can do hydrogen bonding, and that comes back to like dissolves like. If the liquids don't mix, they are called immiscible. So for example, oil and water are immiscible. The reason why is because water is polar, however, oil is nonpolar. So going back to like dissolves like, well, oil is nonpolar, water is polar. That's the reason why they're immiscible, because they are substances that do not have similar natures, so similar polarities. Okay, so polar liquids are going to be miscible in other polar liquids. Non-polar liquids are going to be miscible in other non-polar liquids. Okay, so as a summary of what we've talked about, with solids, if we're talking about temperature, if you increase the temperature, you're going to increase the solubility for most solids. Okay, if you think about something like protein powder and you're trying to mix that into, let's say, some milk, okay? If you use cold milk, it will dissolve a bit easier. However, if you warm up said milk and try to dissolve that protein powder in it, you're going to have a lot harder of a time. So that's why it says for most solids, if you increase temperature, the solubility is going to increase, but not necessarily everything. And with pressure, pressure is not going to have an effect on solids. It only has an effect on gases. For liquids, solubility of liquids are not going to be affected by temperature or pressure. And for gases, the solubility of a gas is going to decrease if you increase temperature. And for pressure, the solubility of a gas increases when you increase the pressure. Okay, so this is actually like a really nice table that summarizes factors that can affect solubility, such as temperature and pressure.